Let's start the meeting. Let me introduce our speaker today, Melissa Pesce-Rollins. She received a bachelor degree in astronomy from University of Arizona in 2002, master's in physics from University of Pisa in 2006, and PhD in physics in 2010, University of Siena. Master thesis was dedicated to construction and testing the Silicon Stripe tracker of the Large Area Telescope LAT on, and the PhD thesis was dedicated to measurements of the cosmic ray electrons and positron spectrum with Fermi LT. Recently, not so recently, Melissa started working on gamma ray solar flare physics with Fermi in 2012. So please go ahead, and you have 5 minutes. I will roughly 5 minutes before the end. And I sent you presenter's privilege so I can show you screen.
Okay, thank you so much.
Please turn on your video also.
Yes. Okay, let me get started here. Okay, so here's my video. Can everybody see me okay?
Yeah.
Okay, hi. And let me now put on my presentation here and put it up, and then I can share my screen. Hold on. Okay, here. Can everybody see my screen okay? Okay, excellent. Okay. So thank you, Gregory, for inviting me to give this webinar. It's my first time. I've never done a webinar, so it's I hope I do okay. So I've been invited to talk to you about the Fermilab observations of gamma ray solar flares during the 24th solar cycle.
Sorry, yeah. A couple of small gray areas are blocking your presentation.
Yeah.
Just minimize everything as I said.
Let's see here. This down.
And remove somewhere down.
Is that better?
Great, perfect. Yeah.
Okay. Yeah, that was starting to bother me too. Okay. So, like I was saying, I'm gonna give an overview of the Fermilab observations of gamma ray solar flares during the last solar cycle. So let's see here. Okay, so first I want to give just a little overview of what the Fermi Space Telescope actually is. And here I have a little cartoon rendering of the actual satellite itself. And there's two instruments on board. There's the gamma ray burst monitor, which is designed to study short transients, so gamma ray bursts, solar flares, and also terrestrial gamma ray flares, and it's designed to study these transients in the energy range between 8 keV and 40 MeV. And it essentially observes the entire unocculted sky. I don't know if you can see my little hand here on the screen, but down here is where half of the GBM is, and on the other side of this of the satellite is the other half of the gamma ray burst monitor, the instruments that make up the gamma ray burst monitor. And this this gray square you see on the top, this is the Large Area Telescope. It's actually fairly large. It's not just a clever name. It's almost 2 meters by 2 meters by 1 meter. So it's a fairly large square, and it's a pair conversion telescope. It's essentially an all-purpose gamma ray observatory, and its energy range overlaps slightly with the gamma ray burst monitor. The light goes from about 20 MeV up to beyond 300 GeV. It has a fairly large field of view, and this is what allows it to be an all-purpose gamma ray observatory. And what's really important, I think, for this presentation is for you to note that we observe the sun only on average 30 minutes every 3 hours. 3 hours is roughly 2 orbits around the Earth. And so the sun comes into our field of view only on average 30 minutes every 2 orbits. So we are by no means a solar observatory. So one might ask, why on earth and why am I presenting work here on solar flares with Fermi if we're not a gamma ray, if we're not a solar gamma ray observatory? Well, I hope to convince you and answer that question with the plot that I'm showing here on this slide. What I'm showing here is the number of solar flares with emission above 25 MeV detected from 1980 roughly up until present. The scale is a little small on the x-axis, but those are years from 1980 to present. And I'm also showing the monthly average sunspot number just to give you an idea of where the solar cycles were. And you can really see that over the past 30 years, there was really limited sampling of solar flares at such high energies above 25 MeV. All of the flares that were detected were associated with very bright GOES X-class flares. There was some excellent work done in particular by EGRIT that detected this extended greater than 100 MeV emission for over 8 hours, which was really surprising and has triggered a lot of interest in the field. And also 3 behind the limb solar flares were detected with energies below 100 MeV. Now, once Fermi was launched back in 2008, the sampling really has drastically increased, and you can see that by that pinkish histogram here on the rightmost side of the plot. We've detected with 45 solar flares with greater than 5 sigma significance over the 24th solar cycle. And more than half of these are associated with more moderate GOES M-class flares, not just the brightest class. We've seen extended emission for more than 20 hours, so extending what EGRIT was able to see. And we've seen for the first time 3 behind the limb flares with emission up to GeV energies. And I've highlighted that with these bright red stars over here. So out of 45 flares, why dedicate an entire bullet on just 3 flares, these behind the limb flares, and a slide in the seminar? Well, they're particularly interesting, and I'm sure the people in this audience know it better than I, but these behind the limb flares really do give us a chance to study in detail things that we don't get to see on disk flares. I mean, in particular, for gamma ray emission processes, gamma ray emission really requires larger densities, chromospheric densities. And the measurements of gamma ray line emission that have been done over the past 30 years are generally consistent with compact region located close to the active region. An observation of gamma rays, both line emission as well as pion produced from behind the limb flares, can really imply 2 things more, of course, but I've listed 2 major points here, is that a spatially extended flare component that can subtend large ranges of heliolongitudes must exist. And in order for these particles that to travel from behind the limb all the way to the visible limb to then interact in the chromosphere and produce the emission that we see at Earth, or which is another possibility that is still up in the air, whether the acceleration and the emission occur up high in the corona that peak above behind the limb where we can see it from Earth. Of course, this does kind of require larger than usual coronal densities in order for it to happen, but it's still a possibility. And I put here this the classic cartoon that Ed Cleaver had put in his paper in 1993, which really, I think, does a really great job of illustrating the idea of the CME allowing for the particles to travel far. So if we go on to the next slide, before I dive into some of the details of what we've seen with the LAT, I really want to spend just a couple slides on describing how we analyze the data in Fermilab, because it is very different from what is usually done in X-rays and other energy bands. So we have 2 essentially sets of ways that we analyze our data. What I call the standard LAT analysis is it's an event classification. So we really see event by event the particles that interact in the LAT. And we have to be able to distinguish between whether we're looking at a genuine photon or background event. So we rely on classification trees to reject the background and to provide to the public, because all the data is public from Fermilat, high quality photon data. Once we have that data, then we perform likelihood fits of both spatial and spectral models around the region of the source that we're interested in this case, of course, the sun. So we typically take a circle of about, with a radius of about 10 degrees around the sun, and there can be several sources within that radius. So we have to be able to model them all before we perform the fit. So there's background sources, there can be actual celestial sources, there's the galactic and isotropic background. The sun itself, the quiet sun, the non-flaring sun, is also a source of gamma rays that we need to be able to model when we're studying solar flares. So we do all of that, and then we're able to provide the results for the best fit models. We found also that the high flux that occurs from hard X-rays during solar flares can cause a pileup effect in our anti-coincidence detector. And this problem was solved by developing a solar flare event dedicated class, and that was released back in 2015. Another analysis method that we use is called the lat low energy, or LLE for short. And this was designed for short transients. In fact, it's most useful for short transients. And it's a more simple approach. We model the background, essentially fitting time series of lat events from region around the sun or the transit you're interested in studying. And this gives a higher effective area at lower energies, for example, below a GeV. But of course, it's a lower signal to noise with respect to the standard analysis. So this is only useful when we have a short transient. But the positive side is that it is immune to potential pileup effects in our anti-coincidence detector. In fact, we used this method before we had developed the solar dedicated event classes to be able to analyze short solar flares. So like any analysis, you want to test for possible emission models that best describe your data. So when it comes to what we do typically with solar flare lat analysis, we fit the spectral data between 60 MeV and 10 GeV, and we try to test for these. We picked out three different emission models. A pure power law and a power law with an exponential cutoff can be essentially phenomenological models to describe bremsstrahlung. And then also templates to describe pi and decay emission provided by Ron Murphy and described well in that paper from 1987. And I'm showing here, here on the left panel, it's about 20 minutes of data from one of the brightest solar flares that we saw back in 2012, March 7th. And we see here the black points are the data points, and the three colored lines are the three models fitting to the data. So we rely on the likelihood ratio test to estimate the significance of the source and whether the curve model provides a better fit. Now, curve model, I mean the number 2, the power law with exponential cutoff. So when this curve model provides a better fit, we also fit the data with a series of these pi and decay models in order to be able to determine the best proton spectral index that describes the data that we're measuring. So now that I've gone into the details of the analysis, I want to give a little bit more, describe a little bit more of this population of solar flares that we've seen with the Fermi-LAT. So like I said, there's 45, so there's quite a few. And what we wanted to do was to be able to somehow categorize these flares that we're seeing. And so what came to mind was, in fact, in a discussion with Albert Shin and others at a Lorentz Center meeting, was to compare the shape of our spectra to what is seen in hard X-rays, the non-thermal non-X-ray signature. So what I'm showing you in this cartoon is when the Fermi-LAT emission has a similar shape and peaks at similar times as a hard X-ray, we say that is a prompt emission. But we have lots of cases where the shape is totally different from what's seen in hard X-rays, or similar but peaks way later than what's seen in hard X-ray. In that case, we just call it a delayed emission. We have cases where we have two delayed components. We have a short delayed component and then an hour-long delayed component, which is shown here in this cartoon on the right. So out of all of these flares that we have 18 with a prompt component that really is synchronized with hard X-rays. We have 37 with some sort of delayed component beyond the hard X-ray, and then I'll go in a little bit more detail on that. Some of them are longer than 2 hours, shorter than 2 hours. They're all different amongst each other. And of course, we have these three behind them flares as well, which are a category in themselves. So I want to spend a couple slides to just show you some light curves so you get a better idea of what I mean by these different classes that I'm using to categorize the flares in the catalog. And I'm going to start with the prompt only, which you see on this slide here. So on the left, this panel shows you the top panel is the GOES soft X-ray flux. The middle panel is the Fermi gamma ray burst X-ray hard X-ray flux. And the bottom panel is from the LAT, and in this particular case, it's from the LAT low energy analysis method. And this is actually the first solar flare that we detected at high significance. It was back in 2010, June 12th. And you can see here from the bottom panel that really the signal does resemble quite strikingly what is seen in the GBM. And this is why we classified this flare as a prompt flare. Now, for all prompt flares, we always look in the following time windows whether there is a delayed component associated with this flare. And that's what you see on the panel here on the right, which it's a zoomed out version of the panel on the right, showing you that we only have upper limits beyond the flare. And so this one is why we classify this one as a prompt only flare. Now, here we have a case of delayed flares. I show two different kinds. And like I said at the start, we don't have the sun always in the field. We don't always observe the sun. So there are cases where there's a beautiful X-ray flare going off, and simply the sun was not in the field of view, so we don't know what was happening in gamma rays. We can't say anything. But we do have some cases where we got lucky, and the prompt X-ray flare was in the field of view, so we were able to observe it, and we were able to say whether there was gamma ray emission or not. And there are 4 cases where we had the sun in the field of view, and we can say with certainty that there was no prompt emission, but there was a delayed component. And these we call delayed only. Unfortunately, for the majority of the flares, we can't say that with certainty because the sun simply was not in the field of view during that short time when it was flaring in hard X-rays. And last, but not, well, actually it's not last, it's second to last, the prompt and delayed class. And these are the ones where we were lucky because we got to see both a nice prompt component and then a nice delayed component moving on. And here I show 2 examples. On the left, you see a case where we have a nice sharp peak, and that's the nice prompt component, and then a softer curve going on for the delayed, but it's a short delayed. It's only about 10 or so minutes. Whereas if you look here on the right-hand panel, this is a very nice flare that was seen in 2017, September 10th. And here we saw a nice prompt component and then emission going on for about 12 hours after the X-ray flare had died off. And we have 10 cases of flares in our catalog where we saw both prompt and delayed component, and we have a chance to study those in detail. And last but not least, of course, these are the behind-the-limb flares. And I'm showing here the most famous and most, I'd say, fascinating behind-the-limb flare seen by the Fermi-LAT. And it's the one from September 1st, 2014. This one was quite spectacular because the active region was over 40 degrees behind the eastern limb. And the emission seen in the LAT lasted for about 2 hours. And it was very significant. It was a very bright source in the gamma ray sky for those 2 hours. And as you see here on this panel, the very top panel, as it goes soft X-rays, and it was completely flat, no signal whatsoever. And in this, but you see the second panel down, the stereo was very bright, a very significant flare because they had it blast on right in front of them. So this was a really nice flare. In fact, we saw GeV energies for almost 2 hours. And this again does really seem to suggest a need for a spatially extended component to allow these particles to travel so far from behind the limb to the visible side of the disk. So going into a little more detail, we were curious to see whether there was anything interesting about the active region position on the solar surface for the flares seen having gamma ray emission and those that were not. Those were just X-ray flares. So what we do here is we compared the M and X class flares seen by XRT, and those are the gray dots that you see here, compared to the ones seen by the LAT, which are the red dots. Now this panel is showing you the latitude and longitude distribution on the sun. And the vertical blue lines are illustrating where the visible limb is. In fact, you see those 3 red dots correspond to the behind the limb flares that we saw. What's interesting here is looking at the latitude distribution, which is this histogram that you see on your right. And you see that the Fermi solar flares are predominantly coming from the northern hemisphere. 64% come from the northern hemisphere, whereas the IXRT flares show the exact opposite trend. They have 62% coming from the southern region, southern hemisphere, sorry, instead of the northern. So that's interesting to see how there is this striking difference between these two populations. And if you take the lat flares and subdivide them into those that have more than 2-hour emission, delayed emission, and those that are shorter, and here you see that in the blue and red dots on these plot, you see that again, the ones that have emission lasting more than 2 hours are predominantly from the north, 80% this time, whereas the ones with shorter delayed emission are pretty much even 50-50 over the latitude distribution. Now, another interesting, I'd say valuable piece of information that the LAT can provide that was not available prior to the LAT from the older space missions was to provide information on the emission centroid of where the gamma rays are coming from during the flaring episode. And so out of the 45 flares that we detected, 8 of these have a localization with 68% uncertainty, less than 360 arcseconds. Now, I know that for the solar community, this is ridiculous. It's huge and it's not something to consider, but we're talking about a paraconversion telescope and the instrument is entirely different. So we suffer from different kinds of limitations. So this is not so bad considering we're seeing emission, the emission is below, it's at most GeV energies, and it's for a short period of time. So this is pretty much the best that the LAT can do in these conditions. And 3 of these flares were bright enough to have localization in multiple windows. We had enough statistics to be able to split it in multiple windows to be able to see whether there was any significant movement in the emission over time. And strikingly enough, 2 of these were the behind the limb flares. So those were really strikingly bright flares for our sample. Now, and here I'm showing just an example of the flare from 2014, February 25th, which was a pretty spectacular flare in itself. And the red circle you see here is the 68% emission centroid from the emission. And I heard a ding. Does that mean somebody has a question? Okay. So moving on, I wanted to show you the example of the localization as a function of time. Now, this is the brightest, longest flare that we saw. This is the one from March 7th, 2012, which had a emission that lasted over 20 hours. And in this case, we were able to divide the data up with enough statistics and see that over time, the emission centroid did move pretty much from east to west across the disk. And unfortunately, this is the only flare that actually shows this type of trend. I think the main, well, we don't have too many flares that can divide into time intervals, but the main point is that the other flare that could have shown this type, that had enough statistic and was bright enough to do it, was the one from 2017, September 10th. But that flare was on the western limb, so we really wouldn't have been able to see any movement anyway because it would have gone behind the limb, and we're not able to see that. So unfortunately, this is the only case that we have that shows this type of trend of moving across the disk. So going into a little more detail and looking at how...
Question?
Yes? Yes?
Does that mean that you looked for motion in the September 10th event and did not see it? Hello, Melissa.
Hi, Hugh. For the September 10th flare, yes, we had enough statistics to divide the data into different time bins and do the localization study. But having it being just on the western limb, it was pretty much always there. The error radius would get a little bit larger, and so you really couldn't say they were all pretty much consistent with each other. It's in the publication now. I can look it up somewhere and send it to you, but the actual, yeah, we tried to see whether there was any movement, but it was all right there on the edge of the western limb.
Okay,
So,
thanks.
yeah, no problem. So Also looking into a little bit more detail on how these gamma ray flares are associated to what's happening in the GOES soft X-rays, we put together these two simple histograms, and you see on the left in gray are showing just all of the GOES flares from the C-class on from the 24 solar cycle, and the blue histogram is showing you the GOES flares that are associated to gamma ray flares seen by the LAT. And you can see that they're pretty much evenly distributed between M and X-class flares. Now, if you take that blue histogram and subdivide it into those that have emission lasting more than 2 hours, less than 2 hours, and also those that only have prompt emission, you see that the results here on the right side of the slide. And you can pretty much see that the flares with some delayed component, again, are pretty much evenly distributed between M and X-class flares. There is no real preference. What is a little more striking is that the ones that here are labeled LLE only, which are the ones that were only seen in this low energy analysis method, so they're really only prompt flares, tend to have to be associated to weaker GOES class flares. These are the ones that have no delay component at all. They're just short, transient, seen in gamma rays. Those tend to be more associated to weaker class flares. Now, I mentioned already several times the idea that these gamma ray flares lasting for hours and these behind the limb gamma ray flares kind of have the need for some sort of spatially extended component. And CMEs have been kind of a very popular, let's say, scenario that has come up over the past years. And so, of course, you look into it and you see whether there is any connection. That's what I'm trying to show on this slide here. Only 3 of all of our 45 solar flares detected are not associated with CMEs. The rest are. You see here on this top left-hand histogram, again, the gray is for all the CMEs from the solar cycle, and the blue are for the CMEs associated with gamma ray flares. And you can see that we are pretty much sampling the higher end of the speed for CMEs. And if again, if you do the same game that we did on the previous slide, if you separate that blue histogram into different classes, you see that, for example, the CMEs that are associated with gamma ray flares that last with emission lasting greater than 2 hours are predominantly associated to fairly fast CMEs. In fact, they have mean speeds of over 1,700 kilometers per second, whereas the flares that are associated to the CMEs that are associated to flares that are just prompt only, and as shown here on the bottom histogram, have a mean speed of 656 kilometers per second. So there really is a division between these two classes. And so if looking, of course, digging a little more into it, you're curious to see whether the fluence is influenced by the CME speed, the fluence for these gamma rays. And that's what I'm showing here on this slide. This is the gamma ray fluence on the y-axis versus the CME linear speed on the x-axis. And again, I've done the same game of splitting them up between emission lasting more than 2 hours and less than 2 hours. And you see that they are correlated. And if you just consider the flares that have emission lasting more than 2 hours, the correlation increases, and I'm showing that here. That's a Spearman correlation of almost 70. And the correlation does decrease if you consider also the flares with lower duration gamma ray emission. So that's another piece of evidence, let's say, in favor of the CME scenario. Now, another thing that I think is interesting to look at is also how the flux varies with time for these long duration gamma ray flares, and that's what I'm showing here. What I did was I selected all of the flares that had a significant detection in more than 4 observing windows for the Fermi-LAT. That way we're able to really sample the shape of how this flux varies with time. And that's what I'm showing in this plot here. And in order to be able to plot them all on the same graph, what I did was I'm plotting the time since the start of the GOES X-ray flare. And note, this is in hours. So these really are long duration flares. So the first thing that you see is that they all seem to show this rise and fall behavior with time. Another striking, I'd say, thing that comes out from this plot is that the peak flux really, they span up to 2 orders of magnitude between each one of these flares. So there really are different flares, different, let's say, faces to these flares. Another thing that struck me when I looked at this plot was how the change in flux from the peak, and I highlighted here, this is the peak of the flux to the end of the flux. For example, for this flare, which is the one from 2017, September 10th, they really change dramatically with time. Look how fast this one cuts off and how slow this one cuts off. This one is from 2015, June 21st. They really do fall differently. The one from 2017 is much brighter and it falls a lot faster with time. This one instead from 2015 is not as bright. It's still a very long duration flare and it's a much softer decay. And there is no connection with the GOES X-ray class. Most of these are bright X-class flares, so there really is no distinction there with what's going on in soft X-rays. But again, CMEs, if you plot, and that's what I'm showing here, if you take a look at how the flux changes over how the time changes, so this is essentially the derivative, if you see that how that changes with respect to the CME linear speed, you see that there really is a positive correlation between these two quantities. And the way that you could interpret this plot is that the faster the CME, the faster the flux drops with time from the peak, from the peak to the end. And so that's, I think, pretty striking and support, I'd say, for what's going on with CMEs. Now, another really nice result that came from outside of the collaboration, from Gopal Swami's paper in 2018, he did this really nice study of comparing the characteristics of type 2 bursts with some of the characteristics from the Fermi-Lat delayed flares. And in particular, he took, for example, the type 2 burst duration and end frequency, and he compared that to the duration of the Fermi-Lat delayed flares. And he only considered flares lasting, I think, 3 or 5 hours, I can't recall. Nonetheless, the ones lasting a long time. And then the results are shown in these two plots here that come directly from the paper. What you see is that there really is a linear relationship between the type 2 duration and the lat delayed duration, and also between the type 2 ending frequency and the lat duration. So this really is strong support that the same shock that has accelerated electrons to produce the type 2 burst is also accelerating the protons that then propagate from the shock back to the solar surface to produce gamma rays via pion decay. But this again is another piece of supporting evidence for the CME shock scenario. So how about the inferred proton properties? I said it towards the start of this presentation that when we fit the spectral data, we're able to also get an estimate of the inferred proton indices thanks to Ron Murphy's templates. And so I'm showing here an example. This is again the bright flare from 2012, March 7th. And the top panel is showing you the GOES, the X-rays here, and also the GOES protons, the SEP events going on after this flare occurred. And on the bottom panel here, the blue is showing you the lat flux as a function of time, and here the red points are the inferred proton index. And what you see essentially is that the proton index evolution softens with time as the flux dimmens, and this seems to be a reasonable result. But if you go here to the next slide, here I'm showing you the results for the flare from 2017, September 10th. And this is a zoom, here on the right is a zoom of the prompt phase of the flare. I remind you that we were able to really sample well this flare because we saw both the prompt and the delayed really well. We had lots of statistics, so we could do a lot of testing on this flare. And here on the right side panel, we show the GOES and RESI light curves. In the middle, we show the lat flux. And in the bottom panel here are the proton indices inferred by fitting the spectral data in the lat. And you see that there is an initial softening with time and then pretty much a flat constant and the proton index. And then if you look over at the left-hand panel, you see the extended phase of this flare. And you see that again, it goes off softening with time. So the data really does suggest that there are multiple phases in the proton index evolution with time. Maybe this occurs in other flares as well, but we weren't able to sample with enough statistics to be able to do this kind of plot. But this is the only flare that we're really able to see convincingly that there are several phases going on in the proton index with time. So of course, it's I was curious, and I'm sure many people also are curious, to take a look at the solar energetic particle properties associated to these gamma ray flares. And there's this nice paper out by Alessandro Bruno that he published in 2018, and it provides a nice summary of all the major SCPs detected by the PAMELA instrument from 2011 to 2014. So it's not covering the entire time range of the solar cycle, but it is a nice big chunk of time that we can compare. And looking and studying his paper, I was able to confirm that all of the SCP events that PAMELA saw and had a fluence, a detectable fluence, above 1 GeV also coincided with LAT gamma ray flares. Also, what Alessandro Bruno did in this paper was to do fitting of the spectra of the SCPs, the time-integrated spectra of these SCPs. And he provides for each one of the events the resulting spectral index as well as the rollover energy for each one of these events. And if you see that the SCP events coincident with the LAT flares with emission lasting longer than 2 hours, they generally tend to have softer spectral index and higher rollover energies. And this is similar to what Bruno et al. Saw for values for GLE and sub-GLE events, also comparing to GLE and sub-GLE events from past solar cycles, given that this solar cycle was fairly poor of GLE events. So I interpret this as whatever is driving these GLE or sub-GLE SCPs could also be driving the high-energy gamma ray events, given these similarities in the results for the spectral index and rollover energies. So how about the flares not detected by the LAT? Because there were 49 X-class flares in the solar cycle, in this last solar cycle, and only 24 of them were detected significantly with the LAT. So what about the other 25? What happened there? So we did a little bit of cross-checking in the data to see whether we could answer this question. Now, only 7 of these 25 were actually, the sun was in the field of view for only 7 of these during the prompt phase. And all of these 7 were associated with either slow CMEs or no CME at all. Again, this provides somewhat of a support, not as striking as from the previous slides, but it does provide a little bit of support for the fact that we might need a fast CME in order to produce delayed gamma ray flares. But a big question for me still remains is that why didn't we see any prompt emission? I mean, these are very bright, strong X-class flares. We should be able to see gamma ray emission at least during the prompt phase for at least these 7 flares that were in the field of view at the time. So that is still a question that needs to be answered. But I tried to put together a little simple scatter plot here to give you an idea of how this data all falls in together. What I'm showing you here is the CME linear speed on the y-axis versus the GOES peak flux on the x-axis. Here again, I'm using blue and red dots to represent the gamma ray flares seen with emission lasting more or less than 2 hours. And now the empty circles are the X-class flares not detected by the LAT. And the filled gray squares are those that were not detected by the LAT, but however were in the field of view at the time of the prompt X-ray emission. And you really do see here that the gray squares all fall well below that horizontal line that highlights the threshold for CME speed above 1,000 kilometers per second. There are a few flares that were not detected by the LAT but had CME speeds above that. And in particular, the one that struck me was this little one that you see up here, because this is a fairly fast CME. This one has almost 2,000 kilometers per second. So it was striking to me as to why we didn't detect this flare. So I went back and dug into the data and checked it out. And what's interesting is that, granted, we didn't see anything during the prompt emission, But in the following time windows, there is a marginal detection. It's about a 3 sigma value detection. It doesn't, this event is not in our catalog paper, which hopefully will be coming out soon, because we set the threshold for 5 sigma significance. But nonetheless, the one single flare here that had a fast CME does have a marginal detection. So again, it all really seems to point at there is somehow need for this fast CME for this delayed emission to occur. So in summary, we have this first Fermi solar flare catalog is coming together. It has a total of 45 high significance flares with emission greater than 30 MeV. There's a wide variety of types of flares. In fact, unfortunately, no two flares are alike. There really are like many children. They're all different amongst themselves. But you can generally classify them into 2 phases of prompt and delayed. That's the best that we can probably do. But the data does seem to suggest that there are at least 2 acceleration mechanisms that are driving these 2 phases. In particular, the prompt emission for the flares that were observed on disk really do suggest that the acceleration is occurring at the flare site, similarly to what is seen in hard X-rays. The lat emission effect is pretty much associated, with the non-thermal signature. It really does look similar to it. Whereas the correlation with CME speed is much stronger for the delayed flux, the longer delayed flux, than there is with the prompt, supporting, again, the CME shock scenario. The relationship with the type 2 burst duration and ending frequency is also another piece of supporting evidence. Behind the limb flares really do need something to allow for these particles to reach the visible disk, and CME could seem to answer that. And also the X-class flares that were not detected by the LAT, again, all seem to point to somehow that the CME speed and the presence of a fast CME is needed in order for these delayed emissions to occur. So that's all I have, and I'm happy to take questions.
Thanks, Melissa. Very nice talk. Perfect timing. We are open for questions, so you can. Hugh?
Yeah, I'll have a question, of course, unless Ed wants to ask one first. Ed Kleiber. But I take silence for assent. So my question is about Ed's cartoon. Melissa, you showed that early on. And, you perhaps didn't notice, but I revised that cartoon in my paper that pointed out the mirror force as a constraint. The revision of that cartoon has the shock wave going out through closed fields, which is another excellent way to get remote excitation. So I urge you to consider that version of the cartoon instead.
Sure. Can you send me the link to that paper so I can take a look?
I think it's in the paper, but I'll send you the cartoon anyway. It's just a.
That'd be great.
Yeah. Okay.
Other questions? All others, other than Hugh, I'm muted. Hugh is also. I wonder. So, what I would like to see or hear at the very end, if you or someone come up with a nice model which would explain all these features by an acceleration, single self-consistent picture. But my question is, what is or are missing links needed to build such a picture? Your opinion?
Well, I'm obviously not a theorist, but I think that it would be a lot easier to be able to put together a self-consistent model to describe what we're seeing if we had more cases where we were able to observe the flare in its entirety. I think that that's one of the limiting pieces of information that come from the LAT, is that we have so many data gaps and that we're not able to really sample fully what's going on. And so I think that it would be a lot easier for the theorists especially to put together a way to describe what's going on with cleaner, not cleaner data. I mean, the data that we have is clean, but I'd say with the data that had it perfectly sampled everything that was going on. I mean, if we had something, a gamma ray telescope that was just pointing the sun and we were able to fully sample all of these flares, I think that a picture would come out, a global overall picture would come out a lot easier than trying to guess what's going on in the gaps. That's pretty much how I see it.
Okay, thanks. Any other questions? So, still.
Another question.
Okay, go ahead.
On the hardware side, I think another thing you want to ask for is better angular resolution, better imaging properties. So how hard is that to do for gamma rays at these energies, do you think?
Well, when the lab was being designed, we had to really take into consideration of some trade-offs to be able to have an all-purpose observatory that could cover such a wide range of energy. So some of the trade-offs were at lower energy, the PSF kind of really does suffer, and that's due to essentially multiple scattering in the actual tracker. And the multiple scattering occurs because we have to have some sort of thick material that helps to convert the photon into electron-positron pair. And we need that because we wanted to also observe at higher energies. If we want to have just a gamma ray instrument that observes, for example, the energy range that is interesting for sun, so below a GeV, we could probably do it with much thinner conversion foils that would allow to improve a little bit the PSF. And then also change the topology of the actual silicon strip detector. We need to have thinner pitch between the strips and to be able to improve also the PSF there. You'd really have to design a new detector, and it'll never really be with the angular resolution that we would love to have, that we dream about in solar physics. Because one thing is, as I mentioned earlier, was even if we do have an instrument that has thinner conversion foils and we're able to really keep into control the multiple scattering, we would need to have a flare that lasted for days to have enough statistics to be able to improve the emission centroid. And also, if we had emission, if we had flares that went off up into tens of GeVs, then we'd have a much better angular resolution for how the detectors develops. But unfortunately, flares really are in that range that is very difficult to improve the PSF.
Sylvia is unmuted, so go ahead.
Yeah, can I just ask a question?
I cannot hear you well. Please be closer to your microphone.
Okay, can you hear me better?
A little bit. Could you do a little bit better job?
Yeah, I'm not sure. Now can you hear me better? So the question is about this slide that you have that you're showing now. So what is your opinion about the mechanism that produces the gamma ray emission for behind the flares?
Get the question? Well,
I think so. Yeah. So you want to know?
Could you just repeat it for everyone? It was not well.
So can you hear me better now?
Melissa, could you repeat the question for people?
Yes. So if I understood correctly, you're asking me what my opinion is, which acceleration mechanism is behind the gamma ray behind the flares. This is how I interpret your question. Am I right?
Yeah, that's correct.
Okay. Well, I think that the most probable way is just that these particles are being accelerated at the CME shock, and then they have access to open field lines that are then connected back to the solar surface, in particular the visible solar surface, where they then interact and produce pion decay, which then produces gamma rays in the classical range. It's just that the biggest problem is finding the way for these particles to travel so far from behind the limb to the visible side of the disk, because that is the most easy way for gamma rays to occur, is if they just interact with a dense surface and produce gamma rays via pion decay.
Any other questions? See any the unmuted microphones, so it's last chance to ask questions. If not, say again that in 4 weeks we won't have everything because it's week of AGU fall meeting and many participants will be there. So the next one will be January 8th. Thank you very much. See you then.
Thank you.
Thank you. Bye-bye.